Welcome to the Input Output Computer Systems Pilot Teacher Training webinar. My name is Corinne Laidley, and I am one of the members of the Computer Science Programs team at PLTW, and I am going to walk you through the fourth grade Computer Science module. To get started, just a quick overview. This module has a little bit of everything from computer systems and how they operate to the anatomy of a computer in terms of how data is stored, how it's displayed, and how data gets transferred. A lot of the information in the first couple of activities can easily be compared to the human body system, which is why this module actually works pretty well with the biomedical science module for fourth grade. So they really work nicely together. Um, the second half of this module, activity three, and the project and the problem, engage students in actual hands-on programming in a tool called Tinker, in which they create interactive games to solve an actual real problem. Um, Before we continue, just a really quick mention of standards and alignment to the grade level. Standards in Common Core and Next Generation Science standards. These are just a few highlighted, but the entire list is available in the framework document and in the standards page in the LMS. We also have the Computer Science Teachers Association alignment, which is very important because this truly is um, dedicated for computer science and has a whole list of standards from K through 12. It's available on their website if you'd like to download the entire list. And they're all divided into different categories. For example, collaboration, computational thinking, programming, and computer and communication devices. So we've mapped it out as well for your reference. And the CSTA standards also are mapped in turn to the math standards, Common Core math standards. Under teacher resources, you will find views of the student view for the LMS as well as the teacher resources. So it's really convenient for the teacher to navigate between both. And all our day-to-day plans are there. And we will be talking about them in the next few slides. Just like every other activity or module, all the activities and the project and the problem are related to one common goal, which is a real world problem to be solved. In this module, the students are going to be motivated to figure out a way to diagnose concussions using a game on the tablet that they will create themselves. So the introduction is again the three characters, Milo, Susie, and Angelina. Milo talks about how he had a concussion and it affected his processing and reaction time, and the students are motivated to try to help diagnose that problem. The focus throughout all the APBs in this module uh, is about collecting data in one way or another, processing that data, and somehow giving back feedback about using, the information collected, giving feedback to the user, whether it's output on the screen or, uh, maybe the vibration of the iPad or making sound, any kind of output from that system. Activity one is does not require any programming. It's mostly to introduce the computer system and compare it to the human body system, focusing mostly on the inputs, like all the senses, processing in the brain and or the CPU of the computer, and output. Also, the students play a game at the end to simulate the input processing output within the computer. For teacher prep, you will need, of course, the iPads so that they can access the activity in Canvas and launch logs. So the launch log will be used throughout the whole module, not just in this activity. So it's good to have per student, of course, one copy per student. And you will need a stopwatch or an app that could, be used for timing the activity. Um, the time that we estimate for this entire activity is about 60 minutes, and students will work in groups at first, and then they will actually they play a game with the entire class, um, where they hold hands in a circle, and there's a starter who starts out by sending a message, which is a hand squeeze, to the person next to them, and the hand squeeze is received, and yet another hand squeeze will move on and on and on throughout that circle back to the starter. So it simulates input, processing that you got an input, and then producing an output and repeating it throughout. So a good way to play that game is probably to do that a few rounds and then maybe average the time that it took per round. And then the second round of this game, or second version, I guess, of this game is to use hand tapping on the shoulder instead of the hand squeeze. And then you can compare the average time for that versus the hand squeezing and make observations. Why would it be different? And how could that be true also about computers? So there's some conclusion questions that will relate to the activity, and always we try to have one that's specific to the activity and one that they can, transfer some of that knowledge to a relatable topic from everyday life. The second activity in this module, again, is not related to any programming just yet. It also involves learning more about the computer system. And to be more specific, it really is about data storage inside the computer. Why do we use binary? Um, how does binary represent data, and whether it's text or images? And then we move on to, in the second part, to learning about data transfer across a network, and how does, in general, how does the internet work? And we do cover a little bit of basic online safety. Online safety, yes. Um, Information highway is also a very interesting activity because it's very new to the students, and there's a lot of worksheets involved, and some games to be played. So we try to keep them engaged in the topic, and hopefully that they would work well together in groups, and it's a good experience overall for the class. The first part of this activity has two worksheets that the teacher needs to print out in preparation for the class. The code intelligence activity, which is teaching them about data representation for text in a computer. And the next one is image decoder, which also teaches them about image representation and how an image is stored in a computer system. After these two are completed, it might be a good break actually. Maybe for the next day, you can spend another 45 minutes. I would think about 45 minutes each part would be sufficient. The second part would be about the internet, about networks, and how they all work and send data and communicate to each other. So um, let's take a look at the human network game. Yes. So in part three, in part two and three, um, it's really focusing on networks and what a network is. And typically, we just want to keep it kind of high level at this age. A network is just, number of interconnected computers that can communicate with each other and can share some common resources like printers or scanners, and internet connection, etc. And we do want them to understand that whenever you're online or in a network, every computer has an IP address that uniquely identifies it. And we do compare a network to a city because they are very similar in structure. At the end of this activity, the students play a human network game where they simulate a network, and all the details of how to facilitate and what to think of and what to print is provided in the teacher's notes. And we always recommend that the teacher preps by reading the teacher notes and looking at the student facing documents just to be prepared for any kind of questions that might arise from the students. When they play the human network game, we are going to divide the class into groups of, 5 or 6 students each. Each group of students is going to be its own network. And this network would have a router. So one student has to be a router. One student will be a printer, and then all the rest will be computers. And for every network, uh, it could communicate with yet another network through their routers. So they kind of are truly simulating some a web of LANs, and understanding how data is going to transfer from a computer to another, whether it's within its network or outside. Each student will have a unique IP address, and the details are provided as to how to do that in the teacher notes. And the students will um, round one, choose to send an encrypted message using these cards on this page that you see. So they will encrypt or encode an image, and this image is going to go to a destination IP address. In round one, the IP address of the destination has to be within that network, and in round two, we take it to the outside of the network so that the routers can communicate. And hopefully, the kids will have fun doing so, as well as learn about the basic structure of a network. Conclusion questions again, and all conclusion questions, I would say, would be best to possibly work first within a group. So let the kids try to answer the questions in their launch logs, write them down, discuss them together, and eventually the teacher would ask them to share their conclusions with the class, and it will make a nice discussion at the end of the activity. Then we move on to activity three. In activity three, we start using Tinker, which is the app on the iPad. So make sure that you have that installed before you start this activity. Um, you are going to focus in this activity on two things. One is keeping in check that the students know that an iPad is just one way to collect data and display data using, well, a tool like Tinker. And another thing is, learning computational thinking skills and programming concepts. So it is about data collection, it is about data display, but also we are learning a lot about how to program, and these skills can be used for not just data collection and display. It's for anything that you want to solve, problems using a computer. This activity is actually divided into 3 parts because it's quite a lengthy activity. It's 3 hours long, estimated to take about 3 hours long. And when you begin, I'll actually like to just show you. Nope, I think I have this open. Sorry. There we go. I'd like to show you the student-facing document. So in this, part one is about why data, why are we even talking about data, and they'll get to understand that data is everywhere today, that we collect it, um, information about your health, we collect information about your school progress. So many things that are out there, social media posts, etc. So the kids are aware of it these days. They know that digital data exists, and we try to show them that data can look like this, which is not very easy to decipher or make any conclusions out of. Or it could, the same data set, be represented in many different ways. So they're given 5 charts where the same exact data set is represented in 5 totally different ways. And they get to make observations about that. And that again serves as a great discussion point where within the group they can talk about each chart and then share it with the class. So that's part one. Part two is where they start using Tinker, and it asks them to navigate to the Introduction to Tinker page. In this page, it is actually a pretty short, maybe half an hour um, mini activity where they are introduced to Tinker. And it is actually fun and engaging activity because they get to kind of play around with Tinker and test things out. So it's not a very formalized tutorial per se because they will be learning a lot in part three. But in part two, we're just, introducing them to how to access Tinker, how to start creating a new project, what does a project entail in Tinker. You are going to have to add an actor or many actors, and each actor can be given instructions to follow, which will create this animation or interactive game. We also teach them how to save their projects because it's really important to be organized and give your projects a meaningful name. Typically, we ask to enter the project um, number and then their initials, all the kids' initials in that group. Okay, another important concept, really, in Tinker, which I would like to talk about, is the grid. So, students will be learning about the XY coordinate system because every object or actor in Tinker has a position. Currently, this actor that you see in front of you has a 0, 0 position, so it's right in the center at the origin of the plane. As you move, you drag your actor about the screen, you will see these numbers here change. Okay, so you see the numbers change, and students will learn that, oh, okay, so these numbers change as I go right. The x coordinate is getting bigger. As I go left, it gets smaller, and similarly for the y-axis going up and down. So they are learning about that. We also give them a nice example without Tinker in mind, just a small grid for them to take a look and understand. Then we show them how to get some help. So in Tinker, you can actually drag a block over to this actor over here. His name is Cody. So whenever you drag an object or a block over to Cody, Cody will explain to you what that block does and gives an example. And then we really ask the students to pretty much play around. Really, this is the best way to learn is to add some code, run it, and make any observations and see what does this block of code really do. Okay, back to the PowerPoint. So, oops. Okay, so in this section, after you learn the basics of Tinker, you are basically gonna move on to creating the game, and which is really the essence of this entire activity. And it is where they're gonna learn the majority of the skills that they would need for the project later on, and then the problem. The activity three is called data collection and display. So keeping that in mind, the game that they're going to design is going to be about this character down here in purple and having to it's going to catch the game is to catch all these four characters that keep falling from the sky. So they fall down the screen, and the player has to tilt the tablet left or right to make the purple character move left or right and try to collide with those falling objects and collect points. So every object, whether it's green, blue, pink, or orange, these creatures will have their own count. And then we, at the end of the game, display to the user feedback in terms of what was the count per color. And we display it actually in a visual chart. So there's a lot going on. They're going to program an interactive game. They're going to learn a lot about programming, and at the same time, they're going to keep in mind that this is actually data that's being collected. So it's input. They're processing that information in variables, and then they're displaying it back on the screen with a chart, which is output. One thing that I would like teachers also to prepare for, in addition to the XY coordinate plane explanation to the students, you also have to probably walk the students through the part of this activity where we teach them how to sense the tilting of the tablet. So a tablet can be tilted left or right, and the X tilt value, it's called the X tilt, it's a value provided to us by Tinker, can range from -1 to +1. If the value is between -1 and -0.2, zero point 0.2, then this means that the tablet has been tilted way left. So we need to move our purple creature to the left. And if the tablet, or the X value, sorry, is between zero point 0.2 and 1, then it's the opposite. It's turning to the right. And if it's anywhere between -0.2 zero point 0.2 and +0.2 zero point 0.2, we're going to consider that as pretty flat, no action required. And of course, as I mentioned, there's a lot to learn here. So they will learn about all these different blocks of code. Some are conditionals, like if else statements. Some are loops or repetition, like a do forever, this block of code. And they will learn about using variables, timers, functions. Um, and the way that the activity has been organized is it's been divided into 6 different parts so that it would be great if the teacher can always check in with them after each step. In fact, when you facilitate this activity, it would be best to have the students work in their group, but then make a discussion out of each step. So at the end of each step, make sure that you know that you can ask the students some questions and get feedback from them, and make sure that they are understanding the material as they go. So if the entire activity is 180 minutes, part one, we estimate about 20 to 30-minute discussion. Part two is another half hour of them practicing to play around a little bit with Tinker. And part three is 2 full hours to make this game. This game is given to them in a lot of detail, so it should be scaffolded well, and students have a lot of guidance in their activity, and a lot of the questions that we ask them to reflect upon, all those answers are actually in the teacher resources, so the teachers can always have all the answers for these discussion points. It's always good to divide your class and give each group a tablet. Groups are usually anywhere between 2 to 4 students, and we encourage teamwork. And in computer science, we call it pair programming. In pair programming, one student is the driver, who is the person using the actual tablet and dragging the code and testing, and the other person or people on the team, if there's more than two, will be the navigators. In other words, they watch over the driver and give him any kind of tips. They can consult with each other. It's a good way to teach collaboration and teamwork on a smaller scale. The way to conduct this activity would be to um, have each student be the driver for one of those steps identified in the document. That would be a great way to make sure that everybody is participating equally, and every person gets a chance to be the driver. The teacher can facilitate this whole activity by using, a projector. I think a projector is a great way to, ask questions and show on the screen uh, discussion points, and talk about the code, talk about how to solve each problem, etc. So it would be great if the teacher can have their tablet projected onto the big screen. Every step that is completed, like I said, please review it with the students and make sure they understand it. And then within their team, the students can actually follow the instructions from the document. It should be pretty straightforward. You can always check for understanding by asking them some QA questions and helping them or talking to them about how they're fixing any bugs that they might have in their code. There are some helpful tips that I would like to show you on the iPad itself. So I will be switching screens in a little bit. I'll be right back to that. And of course, we have conclusion questions again. So the conclusion questions, even though they are, a good way to check for understanding, because they're at the end of the activity, you don't want to wait all the way till the conclusion questions to get feedback from your students. And which is why we really encourage teachers to always be interactive with the students, walking around, checking in on them. And after every step, like I said, please check with them and see if they do get everything or if somebody's falling behind and they can get some help. And when they get help, they can get help within the group, they can get help with another group from another group, or they can get help from the teacher. The helpful tips that I have are things that are a little bit of an annoyance that I saw in Tinker, and I thought it would be worth mentioning to you in case I can help, help you avoid some of the frustration using the Tinker program. It's a great tool, but at the same time, we just want to make sure that students and teachers don't spend too much time trying to debug an issue. So I have my iPad here projected, and I would like to launch Tinker. And okay, great. We're going to go right to create. You might see here that there's a sign in button. This sign in button is actually not going to be used. This is going to introduce a lot more complexity to the way we use Tinker. So it's much easier to just stick with using Tinker as a guest and not logging in. The login option really comes into play if you're using the web version of Tinker. And if you use it on the web, you can create, classroom rosters, and you can check on your students' work, and etc. So it's really nice and well done for teachers on the web. The features within the iPad are a little bit more limited, so that's why we prefer to just stay with, creating accounts. I'm sorry, creating projects locally on the iPad itself. Which reminds me, whenever you start an activity, a project, or a problem, make sure that the tablets are labeled so that you can always give the exact same tablet back to that same uh, group of students. So you have to assign a tablet for the entirety of that project at least. When that project is complete, then sure, you can shuffle them around again and you can change the groups also of the students. But until the project is done, really they have to stick with the same tablet because it's saved locally on that hard drive. Okay, so I'm going to launch my project screen. Shows me all my projects. And I'm going to, for example, start a new one just to show you the process. Create a new project. Every new project starts out with this actor. I can delete the actor by clicking the trash can. And then I can add by clicking the plus sign. I'll add a new character. Let's say I'm going to take a modern and I'm going to add this little girl. You can change the size by using two fingers and squeezing them in or out, moving them in or out. And you can move it around the screen. As you can see, the XY coordinates are changing. And once you're satisfied with where your actor is, you can add more actors. Let's say the penguin. And I would like a backdrop. So you click on the plus sign, and backdrops are in the first row up top. So let's say I am going to pick the outdoors park. Okay, so now this is called the scene setup because I'm just setting up what the scene looks like. I'm not doing anything. If I hit the play, which I will now, nothing happens. Nobody's moving, nobody's doing anything. That's because there is no code yet. So if I click on any of these actors and I click on the wrench tool, it will launch the program area. Now you might hear me say program area or code or script. They all pretty much mean the same thing. So in the program area, you can switch between different program areas by clicking on the actor on the top here. So whenever you click on any of the actors or even the stage itself, the background, you can then add code to that specific actor. I encourage that you as a teacher also play with this, get more comfortable with it so that you can facilitate the class and, answer any questions and feel more confident about it. So a good way to start, I'm going to add over here on the left, there are categories I should mention. These categories are very useful because, especially four of them, because we typically use it all the time. One of them is called the control flow, the yellow blocks. And control flow is basically where you can say, when do you want a block of code to run? I want this to happen when I click the play button, or I want it to happen when I tap on the screen or when I tap on the actor itself. So it's really about controlling the flow of the program, hence the name control flow. Under motion, you can control the movement of an actor. And under looks, you can change the costume, the look of the actor, as well as say something. You can make them have a speech bubble, and in the speech bubble, they can say something. Those are very useful in Tinker. Then you have the sensing. The sensing allows you to see what the x tilde value is, for example. Or you can check and see if an actor is touching another actor, if there's any collision happening. So all these blocks are put in categories that make them relate to each other, of course. And the final one that we use is math. In the math category, you can check for, in addition to adding, subtracting, and multiplying and dividing, you can pick a random number between two, a range of two numbers. You can compare less than, greater than, or equal to, and other things that we probably will not use in this module. So I'm going to get started. For this kid, I am going to add, upon the start of the game, I would like this kid to turn 15 degrees, move, let's say, move 100 steps. So I click here, the keyboard pops up, and I can type in my number. So back to the helpful tips that I wanted to say I've seen happen with me is sometimes blocks don't snap together even though they look like they might be snapped. So for example, over here, when I did this, it might not be snapped if it's like this, let's say, accidentally. Now it snapped. You can kind of see those sparks come up, but sometimes they don't actually snap. And it took me a long time to keep moving my finger around. And then I figured out that, oh, okay, if I actually take the top block, it will snap easier. So sometimes if that's not working, just try the other way around. And to confirm that they're snapped together, you can just drag the top block and make sure that everything is moving with it. Okay, so that's the first one. The second was to test the code from the scene editor. That's right. Sometimes, if, for example, I want to see if this code works, I hit the play button. So I'm going to show you the screen again. If I hit the play button here, we barely saw anything happen, right? I mean, it happened so fast that by the time the screen actually loaded, the girl had already moved her steps. So that's really annoying for a student. They're going to be frustrated by that. So a workaround is to click the back button and be in the scene editor when you hit the play button. So now if I click the play button, I actually do see her move. Okay? So just another option for the students to know that they can actually work from here. Okay, let's go back into the code and look at any other tips that I wanted to mention. Yes, when you're typing in values. So one thing about this is, let's say I want to edit the numbers 15 degrees and 100 steps. I click on 15 degrees. This pops up. You can actually use the um, compass to select a specific, there we go, a specific number of degrees. So that's actually really useful. If I want to say I have two move in a row, or yet more possible, this typically happens a lot with me. If I'm comparing two values, let's say I have two values. When I click on the first value, it's going to pop that keyboard again. As I type in my keyboard, let's say I want this to be 50. And now I want to enter the second value. If I try to click in the second value so I can change the 0 to 100, let's say, it won't let me. You really have to exit out of the keyboard. So you have to close the keyboard. Then you have to move on to the next one and click on it so that you can edit 100. Okay, so if they're getting stuck, just make sure to tell them that they need to close down that keyboard first. Pen up and pen down are used, and then we will talk a little bit about that next. But in this activity, we also are drawing at the end of it a chart because we want to show, display the data that has been collected, all the clicks or the creatures that have been collected. So you will need to use pen up and pen down. And anytime you use pen up and pen down, it's good to clear the screen at the end of the program or at the beginning of the program so that you make sure that everything's been erased before you get started again. Okay, I am going to now show you the code for this activity before we move on to the project. So I'm going to back up and there it is over here. So the goal of this game is to capture the following objects. Everything's been coded here, so I'm going to actually play it to show you what the result looks like, the final project looks like. I hit play and they're falling. I am actually tilting the tablet right now as we speak, trying to catch these creatures. Okay, so 2, 3, let me get an orange one. All right, great. So I keep playing for 30 seconds. At the end of the 30 seconds, the program is going to stop and display results, which should happen any second now. There we go. So the program ended after 30 seconds. It says game over, and your results are 5, 4, 5, and 3. And as you can see, they have drawn a line that is proportionate to the number or the count of that creature. To go back to the code real quickly, I would like to show you the code for all four creatures here is going to be pretty much the same. So when you code one object, you can just drag the code over to the second one. You don't have to recode everything. And to do that, you just drag the top, the first block of each script, and you drop it over um, the next character. Then I can do the same for this actor here. Every script can be copied over to all of them. And then you just, of course, switch over and just make sure that some things have to be updated because they have different positions, they have a different variable to keep track of their counts, etc. But typically, whenever you can drag and drop code, go for it. The code for the creature here that is detecting the tilt is an interesting code here. I'd like to show you as well. It's a forever loop that says, okay, when the button is clicked on start, when I hit the play button, I want to forever keep checking for the tilt of the tablet. So forever, do this forever as long as the game is running. If the tilt value is less than -2, then we have to go left. So we move -100. And then we wait point 2. The waiting is just to slow down the character. If you don't put the wait, the computer is going to keep running that loop so fast that the character actually like flies right across the screen. You won't even see it move. It's that fast. So to slow down the movement of every object, it is recommended that you put a small wait so that you can see the action happening on the screen. I am going to, let's see, go to the stage. The stage code is also different. In the stage code, we have the control of the game, basically, the timer and keeping track or initializing all the variables to 0. So every count has to start with 0. The blue count, the orange count, the pink, and the green. Everything starts out as 0. So does the timer. We reset the timer. So all of that happens in this new function that we created that I called initialize variables. So we call that initialize variable up here at the beginning, which makes the code jump to this block and this is called a function, and run the code there, then go back and continue on to the forever if. The forever if is simply checking for the timer. The timer is actually a variable that is built into Tinker. You don't have to worry about creating a timer. It already exists and you can access that value. It changes every second, it increases by one. So it's a great option for us to use for timing games. Since we want this game to run for 30 minutes, the forever if is checking to see if the timer is now bigger than 30, jump into this if statement and broadcast, meaning means send out a message to all of the actors in this game telling them that they need to stop the game. You actually type in the message right here. And then the stage is going to display the message say game over and here are your results. So whenever you use the word say, the block say, it actually displays a message at the top of the screen. So it's a really nice feature to post any kind of message to the user or maybe questions to be answered on the top of the screen. Actors can also say things. So, for example, I have the actors saying their count constantly so that you can tell how many you've collected of that specific creature. Okay, so when any creature receives the stop game message, so this is called when I receive stop game, then I'm going to stop all the scripts, meaning I'm going to make this creature stop falling from the sky. We're done with that. So it's going to stop this script and it's going to stop this script. Everything in this actor will stop functioning, except for the script that is when I receive. Okay, everything else is going to be stopped. I make it go down to the bottom and draw with the pen. So you have to say pen down. I place the pen down on the screen and I draw by changing the Y value of the character. I'm changing it by the count of that character, how many times it has been touched, right? How many times it has been caught, I guess, by the purple creature, times 50. Now, you might, or students might wonder, why times 50? I randomly picked the number 50. It could have been 50 or 100 or some number, but basically, this number is a multiplier so that when we draw a line, it's going to draw a good sized line that is visible to us. If we are just going to change the y value by the count, which could be like anywhere between 1 and 10, I'm not going to catch more than 10 creatures, then the line is going to be so small that you would barely see the chart. So that is why I created a multiplier of 50 because I really wanted my chart to be visible. So everything is multiplied by 50. All of these are multiplied by 50 times the count. And that pretty much concludes that game. So in this game, they have learned a lot about coding. They have learned about collecting data and doing something with that data. And meanwhile, they are still working on a game that is interactive and fun. And at the same time, it is really actually testing the user's reaction, isn't it? By the user has to tilt. So everything is sort of still related to the main topic, which is the concussion diagnosis. Okay, so that was um, let's go back to the slideshow. That was activity three. After the activity three, which is really the longest of the activities, it has a lot of information. We sort of let the kids do their own thing in project four with some guidance. So, in the project, which is called the reaction test, the game is to develop a game where a actor is randomly moving on the screen and the user or the player has to tap on that with their finger. So again, it is a reaction test. It is concussion related. Everything is concussion related if you think about it. And everything is data related because we are going to count the score for this user and display some kind of fun ranking. You're a tortoise if you're really slow, you're a rabbit if you're kind of in the middle, and you're a cheetah if you're really fast. And they don't really have to stick with those rankings. They can make up any fun ranking system of their own. But that's the gist of it. So in our project, even though it is a project and we're not helping them a lot, we are still giving them guidance and we are still giving them a specific problem to be solved. In the problem, it's going to be completely open-ended. They come up with their own ideas, they come up with their own diagnosis tool rather than uh, us giving them exactly the requirements like we do here. For prep, again, I recommend teachers just reading through their resources. In the teacher resources, we have facilitation notes as well as all the answers to all questions that we might be asking the students as they work through this. And we also have the code, the solution for the project. Students should also work in groups again. Just remind them to be respectful and to work well together as a team and collaborate. And this is a shorter project, so it's 90 minutes long. And it's 90 minutes long. And students will still have to use all the skills that they've used before. So it is a shorter project, but it still entails, all the things that they've learned. It makes them use variables, timers, movement, and looping and all that stuff. So they're really practicing more and more these skills to be ready and more comfortable with it for the problem that comes in next. Okay, as they work through the project and the problem, you will see that there's a lot more recording going on. We ask them to use their launch logs a lot. There are some questions to be answered. In the ask step or phase of the design process, we guide them to ask questions, right? So they have to understand truly the requirements of this project. In the explore, we make them dissect those requirements and think about what kind of code should be used for each and every one of them. So it is kind of like planning in computer science. The explore is let me explore the options I have to program this thing, right? So it is about looking in Tinker and trying to see what works best for each requirement. When you get to the model, you start to actually do the work in Tinker, you build, and when you evaluate is when you test. So you will see that evaluating and coding go hand in hand in programming. So you can't just say go and program the entire thing and then at the end go and evaluate it. That is going to be really hard for the students and for anybody really to get right from the first time, and then it's going to be even harder to find where the bugs are. So we have to work incrementally. You code a little bit, then you go back and you test it and go back and fix it and go back and test again. It really is just a cycle of a lot of build and test, build and test. And encourage the students to do that because we know that students are always going to be anxious to get it done and thinking that it's going to happen very quickly and easily. But it is a lot of work and they could be challenged and a bit frustrated, but encourage them to keep working. And I think that they will truly appreciate it by the end of the lesson, or I sure hope that they do. Okay, so we are going to move on to showing you the game. I'd like to show you the game. So that would be right here. Okay, right here. Okay, I had added this, but I shouldn't. That was just for testing purposes. I'm going to delete those too. Okay, so this project starts out with only one creature. I picked a dragon, and we are going to hit play. Notice how the dragon just is going to move completely randomly across, and I'm supposed to try to get him. I'm tapping with my finger. Let's say I miss, miss, miss. Okay, I got a score of 4. My ranking is rabbit. So this is a great baseline test, right, for reaction time. So um, you can have you know students relate to concussions and to actual sports that they've heard of that seem to have concussions these days, like a lot of soccer, football, and they've probably known someone that's had a concussion. And a nice baseline tool would be something like this, where every student is tested before the season starts and the test results are recorded. And when somebody gets an injury, they can give them the same game again and have them take that test, and then they can compare results with their baseline testing. So It's really a great, fun little game and should be manageable within 90 minutes. As the students code, right, as they write the code, they can obviously refer back to activity 3 code. That's not a problem at all. So they can always refer back. They can talk to each other and they can talk to the teacher. So they could get help from multiple sources. And the activity itself is um, helping them, it's guiding them. For example, there are some things that are new. They've never used the random number generator. So in the code for the movement of this actor, they have to use the random number. So instead of telling them what it is, we just try to inquire them, right? We try to ask through inquiring, where is this block? What do you think the block is going to be? And we help them find it. So, for example, the random number generator, we say, can you find that in the math block? So, in the math block, in the math category, I can go to pi, yep, and I can use the random number generator. The random number generator requires you to enter two parameters. It's the minimum and the maximum numbers. So for example, here I chose negative 400 and positive 400 because I know the x-axis is actually about 1,000 pixels wide. So it could go to negative 500 and positive 500, but I chose to keep it within the 400 rectangle. Same thing with the Y. So the Y values could go it's about 800 pixels tall. So you could go from negative 400 to positive 400. Again, I chose a little bit smaller of a range. I went from negative 330 to positive 330. So we're basically teaching the students to, use the XY coordinates in building this game. There's no way of, other than doing that because it's moving randomly. So this is the only way to make something move randomly is by using the go to XY coordinate block and using random functions. Another new thing in this project is touching the actor with your finger, tapping it. It's called the when actor touched trigger. So they're using a new trigger. Before that, they were checking to see if there was an X tilt to the right or left. Here, instead, the input from the user is not the tilt, but rather a tap with the finger. Same thing on the stage. We have a timer, and this time the timer is compared only to the value 10 rather than 30. And if we get to the timer, if the timer reaches 10, we are going to broadcast to stop the game, which will make the dragon disappear basically. And then we are going to say your score is, and then display the variable score, which we've been keeping track of. Oops, I think I accidentally moved the score. Okay, not working. There we go. So we display the score, and finally, we want to display the ranking. So students will have to use the conditional statements again. If score is less than 4, you are a tortoise. Else, meaning otherwise. If it's not, then we go into yet another branch of if else. And this is going to be if score is less than 7, then you're a rabbit. If neither is true, it's not less than 4 nor less than 7, then you're going to be a cheetah. You're the fastest. All right. So that concludes the code for activity problem 4. Like I said, please refer to the teacher resources. It's a really good document for to answer any of your questions. And we can move on to the last APB, the problem. In the problem, students are given a pretty open-ended problem saying that, okay, well, back to the original introductory story where Milo had a concussion and now all the students want to create some baseline testing game or brain fitness game to assess brain fitness. And there are a lot of ideas out there. So we actually in the document do give the students some recommend or suggestions. They don't have to stick with those suggestions, but it could inspire them to come up with some really nice hybrid of a game or something. The only requirements that we are forcing on the students at this point are three: at least two characters, at least one way to receive input by tapping or tilting, so they get to choose, and a score or ranking system. Everything else is up to them. These are the five game choices that we had suggested. Again, feel free to read through them, but they range from quizzing, asking questions and tapping on the right answer, to random movement, like similar to the project number 4, to identifying options like a memory game, um, and sequencing, etc. So there are a lot of options out there, and I think they're all pretty doable for the students. The only hint that I would like to give to you, and it is in their document as well, I did mention that, is that uh, there is no way to create your own actors in Tinker. Not even text. You cannot create like a big text box that will be displaying questions or answers, like multiple choice answers. So to get around that constraint, right, we can use the say command. So for example, here, what color is this? Let's pretend that this is a question in a quiz. Well, this question has been displayed using this block over here on the stage level. So on the stage, if I actually use the say method, it is going to display it up here. My options, again, have to be below. So I use just any random actors and have the actors say the answer right here. So you tap on the frog if you want blue, and you tap on the troll if you want red. And that's how you can, work around the issue with not having to display text as, a standalone object. To facilitate this, again, this is pretty hands off for the teacher. Let the students kind of explore and walk through the design process. They are walked through it truly step by step in the document, and they refer back to their launch log to answer all the questions. Every section of the design process has its own section in the launch log. Every step, sorry, in the launch design process has its own section. So it's really designed well for their age, and they should be able to move from one step to another and document everything along the way, just like the engineering process or design process will do. Okay, teachers again have to remind them about pair programming, and divide classes into groups. Let them use the same tablet throughout the whole project, which we estimate to be about 3 hours long. And you can make students write in their launch logs, um, and even conclusion questions can be there, and then they can be used as a discussion at the end of class. I really think that the explain step is um, should be two things. They should explain, first of all, their game, what the game is, so they should be able to present it. And I think the students would love to present to the class and show their peers what they've created together. And then not only present the game and how it works, but also talk about their code and talk about any problems that they faced while they were writing the code. And it probably is not complete. They might have not been able to finish the entire project, but at least they can still talk about these issues, and that could create a great discussion with the other the other students in the classroom. This is a sample of the launch log. For example, in the model section, they can write down all their ideas and then pick from the best idea that they have to start developing. Of course, conclusion questions at the end are a great way for discussion and for checking for understanding as to assess them as a teacher. The last thing for assessing is the check for understanding uh, assessment provided to the teachers. You can print that and distribute it at the end of the module and see how they do. The check for understanding in this module is 3 pages long, um, but it's only 4 questions. Uh, the first question is about inputs and outputs, and it's very, very similar to what they have seen in Activity 1 because they get to see actually a video. There's a video presentation in Activity 1, and in that video, they will learn a lot about inputs and outputs and how do they compare to the human body system. Question number 2 is all about information and about data representation within the system, the computer system. and about networks. So it's fill in the blanks with a word bank provided. And then you have the last question is about programming. Question number three is about data, by the way. Sorry, charts. This what you see here. There's some charts to read and make conclusions about. And question number four is the computer programming, the programming part. All the answers, of course, are provided in the answer key. And that should really conclude our module. I know it has a lot in it, but again, if you can keep, step back and look at it as a whole, it really is all about gathering information through input, taking that information and making sense out of it, and displaying it back with some kind of a result, which is output. And it ties really well with with the BMS, the biomedical module, because their module is also about input and output systems, but this time it's the brain being as a computer, functioning as a computer. So they really tie in very well. It is recommended that this module be taught before the BMS module. So they can tie everything in pretty well. But if that wasn't the case, that's fine too. At the end of the or the conclusion of this, we would like all our pilot teachers to give us some feedback. We really appreciate that. On the PLC, you can go to discussions and answer some questions. There are surveys for each APB, so APB specific, and there is a survey at the end for the entire module as a whole. We'd like your feedback because truly that is how this program will get better, and it will be a great thing not only for the program but ultimately for the students' experience. So we really appreciate your help. I hope that this presentation helped you out. I think that you know the students have a lot to learn, but even though they will be challenged here and there, they will feel very rewarded, at the end by creating their own artifact. So I hope you have a great experience in your classrooms, and we look forward to hearing your feedback soon. Thank you.